Welcome to Study Loop.
So they want us to find the wavelength of the third harmonic. This is very simple because the wavelength of the third harmonic, or rather, the wavelength of any harmonic is going to be equal to 2 times the length of the string time over the whatever harmonic it may be. So over that n being a element of the set of all integers. So n can only be an integer, and we're trying to find the third harmonic. So this will be 2L over 3, and this will be 2 times 1.2 meters over 3. So the wavelength of the third harmonic is simply going to be 0.8 meters. And then it's saying now there's another 100 Newton ball. It's being replaced by a 500 Newton ball. This is what's creating the tension in the wire. So if this ball is being replaced by a ball that has more mass, what's the change in wavelength of the third harmonic? So we can say that the Young's modulus can be related to the force tension, whatever that force may be, times the length of the string over the area, the cross-sectional area of the string, and then times the deformation or the change in length of the string. So we can say that the change in length of the string is going to be equal to the force times the length of the string divided by the cross-sectional area times the Young's modulus. And we know that the area is going to be equal to pi r squared, or pi d squared over 4. Young's modulus is simply how it's also called the modulus of elasticity. It's simply how resistant a string is, or any material really, how resistant it is to deformation. So F over A, that's a pressure, and then L over change in L, that's a strain. So this is simply going to be basically how resistant it is to deformation, given that we're putting a much heavier ball at the end of the string. So now we can say, okay, let's plug this cross-sectional area into this delta L. So we'll have delta L equals 4FL over pi d squared y, and they give us the Young's modulus. So we'll have 4, and then we're replacing it with a 500 newtons. We're replacing it with a 500 Newton ball. However, we had a 100 Newton ball before, so we have to subtract that. That's going to be the difference essentially, and then this will be 1.2, the full length of the string or of the beam, and then we'll have pi. The diameter will be 1.024 times 10 to the negative third. Squared, and then the Young's modulus is simply 11 times 10 to the 10th pascals. And we find that the deformation is going to be equal to 0.00530 meters. Now, we're not done yet. We have to find the change in wavelength of the third harmonic. So we can say the change in wavelength of the third harmonic is simply going to be 2 times the change in length due to deformation divided by 3, because it's going to be the third harmonic. At this point, we can just substitute. So 0.00530 meters divided by 3. And the change in wavelength of the third harmonic will be 0.00353 meters, but if we want to convert, we can say 3.53 millimeters. That'll be the change in wavelength of the third harmonic. This will be your answer for part B. And that's the end of the solution. Thank you for watching.